Look at molecular geometry, problems 1 and 2. First one's kind of a complicated problem when it gets to polarity, so we'll look at that in particular. But the first thing we want to look at is for dihydrogen sulfide, so H2S. First thing we want to do is be able to draw its Lewis structure. Please remember that sulfur has 6 electrons around it, leaving it 2 bonding spots. Hydrogen has the 1 electron, so that means each hydrogen is going to share 1 of its electrons. With the sulfur, draw the other hydrogen here, it's going to share its electron forming bonds. So the way we draw this, S is going to go to a hydrogen, it's going to go to a hydrogen. And the reason I'm showing it in that formation is I don't want people to think, I don't want people to draw it like this to give you a false sense of symmetry. I'd rather draw it like I have up there in the answer. This gives you a false sense of symmetry because remember, whenever you have 4 things bonded, or I should say lone pairs and bonds, and you have 4, remember this is going to be a tetrahedral shape. This is not going to be a nice planar shape here. So this right here looks like it's symmetrical, even though it's not. So I tend to write it the other way to make sure you get the idea. It does not have that symmetry. So the molecular shape here, all we have to do is look to see it has 2 bonds on the sulfur, and we have 2 lone pairs. When we have this, we get what's called a bent shape. Now the bond angles for a bent shape, where we also have 2 lone pairs, it's just like water. It's 104.5 degrees. That's something we discussed in class and something you're going to have to just know, memorize. And finally, polarity. Polarity gets to be kind of interesting because if we have sulfur and we look at the electronegativity of sulfur, that's going to be equal to 2.5. And when we have hydrogen, and we look at the electronegativity here, that's going to be equal to 2.1. Listen, when we're looking at molecular polarity, this is not bond polarity, but molecular polarity. Look first to see, is there a difference? And in this case, there is a difference. The difference is 0.4. It's not 0. So in this case, you will have polar bonds. So when we have polar bonds and we have the lone pairs, for the geometries we're going to study, we are going to end up with polar molecules. The reason is it makes it non-symmetrical. Remember what I said here, this is 3D. If you really wanted to draw a good picture of this, you could draw a lone pair up top. Remember the dotted lines indicate it goes back into the board. Then I come out here. This little triangle indicates it comes out of the board. And then finally, on this side, I have a hydrogen. We definitely get a positive side. Remember the sulfur has the more electronegative, so that leaves the hydrogens a little bit deficient. And we definitely get a negative side to this on the opposite side. So that will create a polar molecule for that one. So those would be the answers for number 1. Number 1 is actually one of the harder ones for polarity. And the next one, we're going to look at carbon tetrachloride. And in carbon tetrachloride, remember the carbon has these 4 bonding sites, that has 4 electrons, and each of the chlorines has 7 electrons around it. So it turns out each chlorine will donate an electron, each carbon will also donate an electron to form a bond, and the Lewis structure for this one, we'll have the carbon in the middle, we'll have the chlorines, with their electrons around them. Remember with Lewis structures, you always draw those. This one's going to be a little harder. And fit the electrons in there. So that is a carbon tetrachloride. Now the shape for this, on the carbon we have 4 bonds, and we have 0 lone pairs. The shape for this will be tetrahedral. And since there's no lone pairs, this is going to take the standard tetrahedral bond angles of 109.5 degrees. And then we ask ourselves, is this a polar or nonpolar molecule? Well, you notice there's no lone pairs on this. The carbons bonded to chlorines. It's a very symmetrical molecule now. All of the molecules, or all the elements that carbon is bonded to, they're all chlorine. So the electronegativity differences will cancel each other out with this symmetry. So that is definitely a non-polar molecule.